Hello, my name is Frits de Mul and I would like to show you how to calculate the capacitance of a capacitor with a dielectric filling. And we start with a complete filling. This is an overview of the available presentations, and here is the presentation for capacitor filling, complete or partial. Suppose we have available a flat capacitor with a surface area A, distance of the plates D, and it is empty at the moment. So the epsilon R is 1, dielectric constant. Let's assume that initially the plates are charged with plus and minus Q. And the question is, what will happen with the charge density, the electrical field and displacement, the potential difference and the capacitance when we completely fill the capacitor with a dielectric material. Important is, does the capacitor remain connected to the battery or not? And the case A we will discuss is yes, and in case B it's no. The consequences are, in case A the voltage will remain constant, and in B the charges will remain constant. How do we approach our solution? Let's assume there are no edge effects and that the distance D is much smaller than the plate dimensions. So the consequences are we have no leakage of the electric field and there is planar symmetry everywhere. And that means that Gauss' law is applicable. What are the relevant variables? It's the charge, total, charge density, electric field, displacement, potential difference between the plates, and C, the capacitance. We have material constants, epsilon naught, epsilon R, A and D. And the task is, let's establish the relations between the variables. What are these relations? We have a relation between the free charge, the charge that can be delivered to the plates or removed from the plates, the free charge, and the displacement, and the relation between those is the Gauss law. Material constants give us the relation between the displacement and the electric field. The potential is the relation between the electric field and the potential difference between the paths, the plates, and then the relation between the potential difference and the charge, that's the capacitance. These are the four relations. First, Gauss. Let's take a so-called pillbox with top and bottom. The surface area is dA and the enclosed charge is sigma free times dA. And then the surface integral over the displacement reduces to the scalar d times dA, and it means that the displacement is equal to the charge density, the free charge density. Now for the electric field and the potential, here is the relation between the two. We take the integration path from bottom to top, the length is d, and it means that the integral from bottom to top is E times d, and it means that the potential difference is the electric field times the distance between the plates. Now let's do the calculations. Here is an overview of the relations with the relation between Q3 and D, between D and E, between E and V, delta V, and between C and Q. First, case A, capacitor will be connected to the battery. Well, where do we have to start? We know that in this situation, case A, the potential difference will remain constant. So, when we discuss the variables here, we have to start with the delta V. The delta V remains constant. Using this relation here, we can see that it means that the A remains constant. The relation between D and E means that when now there is an epsilon r larger than 1, means that the D will increase. D will be epsilon r times S large. Of course, the same holds for the sigma because of this relation, the charge density. And then it will hold for the charge itself, Q free. And finally, when you look at the sigma bound, first the capacitance, it means that when Q is enlarged but V is the same, then the C will be enlarged, also epsilon r times S large. And now the bound charges, that's the epsilon r minus 1 times sigma free. That's the extra charge that has flown from the battery to the plates. Now the case that the capacitor is not connected to the battery, where do we have to start now? Now we have to start with the Q, because the Q, the total Q, will remain constant. So, the Q will remain constant. This means that the sigma free will remain constant. No charge is flowing from the battery because it's not connected. This means that the D remains constant, but the E is epsilon r times S small, according to this relation here. This means that the delta V is epsilon r times S small. This means that the C is epsilon r times S large, because of this relation here. And this means that the sigma bound is minus 1 minus epsilon r times sigma free. So that's negative. Conclusions. If the capacitor is connected to the battery, the delta V potential difference will remain constant, and thus the E will remain constant, the field strength. This can only be achieved when the charge is larger, and this means that the capacitance will be larger. If not connected to the battery, the charge will be constant, and this means that the sigma free and the D will remain constant. But the consequence is that the electric field and the potential difference will decrease, and since the potential difference will decrease, the C will increase, and also the C will larger. And this is the end of the talk.